Good morning, everyone, and welcome to the first talk in our applications track. So, little correction, the data science track will be tomorrow here. So today it is the applications track here. I'm very excited to welcome this first talk because I think it really underscores what this entire track is about. We have the pleasure of having Ayman, a distinguished architect at Yahoo, join us to really talk about what kind of applications you can do with Spark. So please join me in welcoming Ayman.
Thanks, John. Thank you very much. Can everyone hear me at the back? No? Is my mic on? Okay, good. Okay, so good morning, everyone. Thank you so much for being here this morning. And first things first, I want to apologize for the title. The title has changed, even though in the initials it said 3 trillion combinations. It actually, now it's 26 trillion combinations. So it keeps getting more and more. So today I'm going to talk about making app recommendations at scale for users. Here's the overview of my presentation. I'm going to give a motivation. Why do we care about this problem? Why is app recommendation such an important problem? I'm going to also talk about the social implications and the welfare for the community. So this is not just an exercise in technology, but it has some really important social ramifications. And then I'm going to talk about how we use Spark to do that. In particular, I'm going to talk about 3 different components of Spark. The first one is collaborative filtering. How do we use collaborative filtering to do that? And then how we leverage 2 key components of the Spark technology. The data frames, and how data frames make a lot of the operations that we do extremely efficient, and then using a very specialized operation within the Spark, which is the blast-free matrix multiplication. This last component allows us to really scale this up and do those 26 trillion combinations in a very, very efficient time. And then last but not least, I'm going to give the results of our experiments and our work, lessons learned, and how do we proceed from here. So the motivation, I just want to show of hand. How many people here don't have a smartphone? Good. How many people here have never downloaded an app from the App Store? Okay, so my job is to convince you to download an app from the App Store. Okay, how do you guys discover apps? How do you know which apps to download? It seems like a very simple problem, but it's actually much more complicated than it sounds. Because if you look at the number of apps, today there's over 1.5 million apps on the App Store and the Google Store. The idea of trying to discover those apps is a horrendously complicated task. Users spend a lot of time trying to find which apps to use. They download apps, they try them out, they don't like them. So there's a lot of inefficiency in doing that. So from a social implication, just by trying to recommend apps to users that they're likely to use, this can have a huge social implication. So imagine, for example, that you can just save 1 hour for every person who has a smartphone. That would translate to about 1 billion hours. That's a huge social impact. So this is something that I personally feel very proud about, that if we can actually save 1 billion hours for humanity, that's something worthwhile. The way we do this is that we try to look at explicit signals that users are using to try to form the base of foundation. So the signals that users are using come kind of 2 forms. One of them is an explicit signal. So you go to the App Store, for example, and people rate apps. And you can actually use this information. The other one is an implicit signal. So how do people are actually using the app? So when you use the app on your iPhone, we can actually record, for example, the time that you've used the app, how many days you've used the apps, how many sessions you used the apps. If we can actually collect all this data, we can have a very detailed view of how people are using the apps, and we can use this as the basis of our recommendation. Of course, the question is, how do you get this usage data? Fortunately for us at Yahoo, we have a way to do this through the mobile analytics platform Flurry. So anyone has heard of Flurry? Okay, anyone has heard of mobile analytics? Okay, so mobile analytics is essentially an SDK that resides, that the app developer uses to instrument their apps. Why do the app developers care about this? Because this allows them to get a better understanding of how their apps are being used. So for example, at the very highest level, I want to know how many users are using my app, how many users stopped using my apps, What is the average session time? How many days in a month the users are using my app? But then it can also get into much more detailed information. So for example, if you're a game developer, you might ask how many of my users reach level 3? How many of my users make a payment? How many of my users make a purchase? So all this information is logged through the Flurry SDK. So the experiments that we did, the results that I presented, and hence the difference in the title. When I first submitted the submission, this was in March. But we did an experiment where we looked at the data from September 1st to September 15. We collected usage data. And we restricted the analysis to the apps that were used by 100 or more users. So there are a lot of apps that are used by 1 or 2 users. Those are highly experimental, very early stage apps that we didn't particularly look at. But even the numbers then are really significant. There are 496 million users. And even after restricting the apps to 100 or more, there's about 54,000 apps. Does anyone know how many users Netflix has? Quick show of hands. 40 million. So this number is an order of magnitude more than the Netflix problem. Netflix doesn't have 54,000 movies. So just to give you a scale of this problem, this is a much larger problem than the Netflix recommendation problem. Here's the data summary. The user count was 500 million, about 500 million users. We had initially 154,000 apps. After we restricted the analysis to apps that were used by 100 or so users, we were down to about 54,000. The training time for us to train the models was 52 minutes. The prediction time to do the 26 trillion recommendations was 8 minutes. I just wanted to say 2 numbers about this here. First of all, people often say that one of the problems of doing predictive models and econometrics at scale is, why can't you just use a sample? I mean, why do you need to go 500 million users to build the model? There are 2 answers to this. First of all, in order to do this, you need to make sure that your data doesn't vary by the sample. So even if I could sample and get a small set, I need to make sure that the results are not going to vary. The second part, which is very important, is that even if you can have a model that was trained on sample, you still need to do the 26 trillion recommendations. So there is one part which is training the model. There is the other part which is actually doing the very large number of combinations. In order to do this 26 trillion combinations, you need to do something that really scales up to 26 trillion. And to the best of my experience, the only way to do this is Spark. Our approach was to use a collaborative filtering-based recommendation system for discovering the apps. And what we did is that we developed a collaborative filtering that works at scale. Nice thing about collaborative filtering is that it gives you a way to project, essentially, the users and the app. So if, for example, in the Netflix, it was the users and the movies. In our case, it's the user and the app. It allows you to project those 2 vectors into 2 low-dimensional features that are compatible. So for example, you can project it into a 60-dimensional space or a 50-dimensional space. And then if you want to get the affinity of a user for an app, all what you have to do is that you have to do a dot product. But this dot product is easier said than done, because again, if you look at the number of combinations, you will get 500 million users, 50,000 apps. So in order to do those dot products at scale, that's quite a challenge. So the way we address this problem and the scaling of a problem is that we use Spark. So collaborative filtering. Collaborative filtering, I'm sure a lot of you are familiar with, is essentially a way to look at a recommendation. So I actually borrowed this directly from the Netflix, where you have your rows are users and your column are movies. And entry ij is how much does user I like app j. And the whole premise of the collaborative filtering is that this is an n by m matrix. So for example, my n is 500 million, my m is 50,000. I can actually decompose this matrix into 2 much smaller matrices, an n by k and an m by k matrix, such that if you take the dot product, if you take the product of those 2 matrices, you can faithfully reconstruct the recommendation. So the point is that I don't really need to know what every user looks at every app. If I just know the user and the app, I can therefore construct the combination. First question that comes to mind is, well, how many latent features do you have? How do you know the number of latent features? In order to do this, we looked at the out-of-sample recommendation. One of the problems with collaborative filtering is that it doesn't allow you to do cold starts. So if you've never seen a user before, you cannot actually do a recommendation for the user because you need a feature vector for the user. So what we did is that we looked at users who had 20 or more apps, and then we randomly pulled out 10 apps from the user. We then trained our model, and then we tried to score the 20 or so more apps on the user. So I said, assuming that you hadn't used those 20 or more apps, can I actually accurately predict how much you're going to be using those 20 or more apps, even though I've never seen you? And what we did then is that we varied the number of factors that we had. So we started by 10, 20, so forth, and we kept increasing them. And you see, as we increase the number of factors, the accuracy increases, and then after a certain point, it drops down because of the overfitting. We found that the number of the optimum number was about 60. And 60 was an interesting number because it roughly corresponds to the number of app categories in the App Store. So intuitively, it does make sense that you can actually decompose the user's interest into 60 dimensions. So for example, social, gaming, travel, utilities, and so forth. As I mentioned, we used a number of the Spark features to help us do this. And one of the most important features that we had to use was the data frames. It's quite often that you need to do joins when you do a lot of these applications. So for example, one of the things that we wanted to do was we wanted to filter out all records where the app was used by less than 100 users. How do you do this? One way you can do this is that you can actually just do a join. The problem with doing this join is that you're not really leveraging any information about the size of the apps, about the relative size of the data sets. Recall that we had 50,000 apps. That's it. The number of records where each record is a user cross app was in the like hundreds of millions. So if you don't leverage this difference in scale, you're really not doing yourself a favor. Before using Spark, I actually came from using Pig, and one of the things that we used to do at Pig was doing a replicated join, where you explicitly say that if the data frames are different size, I'm going to use a replicated join. So the first thing I did is that I actually tried to simulate a replicated join in Spark. So what I did is that I broadcast all the apps that I had across all the nodes. So you see this broadcast statement. And then I actually filtered the apps. So this is like the set here for the lambdas in the set. So this is your way of actually doing a replicated join in Spark, in an RDD. And I was using Python, by the way. But then I realized that the problem with this is that every time I have to worry about that. So fortunately enough, I learned about data frames. And the nice thing about data frames is that you don't have to worry about any of that. So here's how we implemented this in a data frame. So I have here the maximum apps is equal to 100. So first of all, I look at all the apps that I have, so the first line here, and I transform it into a data frame. I then register the data frame as an SQL query, which allows me then to do an SQL query against it. So this is the register here, SQL context. And then I group by the app ID. So now I have all the records. The records that I have is user, cross app, cross the time that they used. So I just group by the number of users. And I issue a very simple SQL query, select app ID, and then the average value, and then the count star. So now I've issued an SQL query. And then after I do that, I filter by the apps that were used by more than 100 users, which is the max apps. So you see 1, 2, 3, 4 lines. And then the last line is that I do a data frame join. That's it. So the simplicity of doing this at Spark is amazing. You don't have to worry about the relative sizes. You don't have to worry about using different SQL. In 4 lines of code, I've done something that previously I would have used, maybe without exaggeration, 100 lines of Pig to do that. And I also didn't have to worry about the relative data size. The data frames automatically does this for me. The second issue that we had to wrestle with is the huge number of combinations of 26 trillion combinations. If you look at it, the number of combinations is astronomical. The collaborative filtering application within Spark has a default predict called predict all. So you can actually train a collaborative filtering model, and then if you want to look at all the possible combinations of user cross apps, which is exactly what we want, because for every user we want to get all the apps that we've used, you can do a predict all. When we tried to do this, it never completed. It just ran forever and ever. When we did the diagnostics, what we found is that most of the time it was actually spent on reshuffling. What was happening is that the users were distributed across all the executor nodes. The apps were distributed across all the distributed nodes. And what was happening is that we were losing time in the case where it's least efficient, which is actually transporting data across nodes. And that's the problem anytime you do a reshuffle. The key to addressing this is to note that, again, just like in the case of the data frames, that the number of apps is much less than the number of users. I only had 50,000 apps. I had 500 million users. Can I exploit this huge difference in size to better predict the users? So what I said is that, let's look at the number of apps that we have. The number of apps is much smaller than the number of users, 50,000. 50,000 can actually be even stored not only in memory, but in core memory. And that's exactly what the BLAS. BLAS stands for Basic Linear Algebra System. 3 is the level 3, which I'll talk about a little bit afterwards. This is exactly what it exploits. So the way we did this is that we broadcast the apps to all the executor nodes. So every executor node now has a copy of the vector of the apps. So there's now no need to reshuffle between data. So you don't need to transport apps across nodes. Every node now has all the apps. And then we used the BLAS matrix multiplication. And using the BLAS matrix multiplication allowed us to get a much higher order of efficiency. BLAS is the Basic Linear Algebra System 3, and what it does is that it solves problems of the general form. A matrix D is equal to the product of two matrices A and B, each one potentially scaled by an arbitrary constant, plus a matrix C. What BLAS 3 does under the hood is that it does two things. First of all, it realizes that if one of them can be cached into L2 cache, making it much more efficient. The second thing that it does is that it exploits the fact that doing a matrix-matrix multiplication is much more efficient than doing repeated matrix vector multiplication because it actually factors the matrices. There's a lot of work that has been done in terms of the BLAS 3, and it's an extremely efficient system to try to do those matrix multiplications at scale and very fast. So this is what we decided to leverage. Again, this is something that using Spark allows you to do that. Using Spark, I was using the PySpark, and therefore I was using the NumPy library. The NumPy library is based on the BLAS 3 system, and therefore it exploits this. So the way we did this, a few lines of code, so you import NumPy, and then you see that the first line, which is my model, essentially after you fit the model, you get the model. And then you get the product features. Product features are the apps. This is like a leftover from the Spark terminology, so you get the apps. And then you collect them on your driver. You do a matrix transpose, and then you broadcast them to all the nodes. So this is the broadcasting. Then the other thing is that I coalesce the user features into 100 RTDs, just to limit the number of reshuffles. And then I do a matrix multiplication. So essentially, all what it is 3 lines or 4 lines of code to do that. Extremely efficient. You don't really have to worry about the matrix sizes. All this is done for you under the hood. And this is, again, something very much like the data frames, where just by knowing the difference in sizes, you can get many orders of magnitude of efficiency. OK, so having said that, what do the results look like? So what we did is that we looked at the recommendation for a specific app. And the app that I used was Tumblr. Anyone here uses Tumblr, by the way? OK, thank you. OK, so Tumblr is a company that was purchased by Yahoo. And when we looked at the recommendation, we saw that the recommendations were bimodal. So there were users who were likely to use the app for a smaller number, but then a lot of other users were unlikely to use the app. And that kind of makes sense. If you take like 500 million users, chances are very few of them would be interested in any specific app. So you see you have this bimodal distribution. We now examine each one of those two modes separately. So we look at the user who had a positive score with like a high score, we see that it's almost a normal distribution. So even within the users who are positive, some of them are more likely to use it, some of them are less likely to use it. And the same thing for the users who had a negative score. Some of them don't like it, some of them really, really don't like it. Okay, so after we've done that, what is the value of a recommendation? I mean, the only reason we're doing this is that we're trying to do a recommendation. What is the value of a recommendation? And this is particularly interesting for me because I don't come from a machine learning background. I come from an econometrics background. So for me, I really care about the difference between correlation and causation. So imagine, for example, that you have a recommender that says, so let's go back to the users who have a very high score. So those users, I have a very high probability that they're going to actually install the app. What if I actually recommended the app to those users? Do you guys think they're going to use the app? So someone is very likely to use the app, and you recommend the app to them. Are they likely using the app? Yes, probably, yeah. Did they use the app because of a recommendation? Who knows? I mean, those users, because they are very interested in using it anyway, might have actually used the app irrespective of whether we got the recommendation or not. And therefore, to try to assess the causal value of a recommendation is a very different thing than trying to look at the correlation. So what we're doing is that we're doing a factorial design. We're doing a 2x2 design. So we're looking at users who have a high score, and we're going to show them a recommendation. We're going to users who have a high score and showing a placebo ad, so a recommendation for another app. We're going to take users who have a low score and then show them recommendation. And then this is the type of users who have low score and show them a placebo. So we have this 4x4 factorial design. And then we're going to actually run the experiment and collect the data. Running the data, I had some problems. I was hoping to present some of the results of the live experiments. We had some experimental problems. But the whole idea is that after you run the experiment, you get the data, who installed the app, and then you try to do a regression model to estimate the causal impact of the treatment, which is showing the recommendation. In order to do this, you need to do a regression. But this regression is a little bit different from the machine learning regression because you're not really interested in prediction. You're interested in the significance of the factor. You want to ask the question, does the variable that represents a recommendation, is it positive and is it statistically significant? What is the causal impact of that? In order to test this, you need to get an idea of what is the standard error and the variance of the estimate. This, unfortunately, is something that is lacking in Spark. So in future work, what we want to do is that I'm really interested in building a Spark's econometrics library. Kind of different from the machine learning, but look at some concept, for example, like the standard errors, robust errors, instrumental variables. There's a lot of things in econometrics, and when you go into the realm of descriptive and general models that don't necessarily align with the predictive models. We're also doing online experiments, as I said, and hopefully we'll have some results very soon. One of the features that we used is the average, the session length. How long did the user use the app? We're also trying to look at different features. For example, what if we just use the number of sessions? How many sessions the users have had? We can also look at the days used. And last but not least, we're looking at the logs of the day used or the log of the time. Because imagine, for example, that if someone has used the app 100 minutes and 101 minutes, those are probably the same. This is very different, for example, if someone has used the app for 4 minutes and 5 minutes. So the difference between 4 and 5 and 100 and 101 could be much larger. So we're actually doing in this, we're trying to do different ways to get the implicit rating of the users. So in summary, we look at a very interesting problem, very relevant problem, which is the app recommendation. We're leveraging the Spark technology, and I strongly believe that if it hadn't been for Spark, we wouldn't have been able to do this at this scale. We're following this with an actual online randomized experiment, and then we're following the randomized experiment with an econometric analysis to ascertain not the correlation, but the causation of the recommendation. So with this, I stop, and I have about 5 minutes for questions. Thank you very much. Can you please take a mic? Sorry.
I was just wondering, for the placebo, would that be an app that you wouldn't recommend? Or
For what, sorry?
In the high score versus recommendation, high score, placebo, low score, the 2x2 matrix.
Yes.
Is the placebo...
So the placebo can be anything. All what you want to do is that you want to know that this user could have seen an app. So I could send them a recommendation for another app, as long as it doesn't interfere with a Tumblr. So for example, if I actually give him something for Facebook, that would not be considered a placebo because those two stimuli interact with each other. If I give him a placebo for a game, that could work. If I give him an ad for a coupon, that will work. For Uber, that will work, as long as it doesn't interfere.
So as long as they're in different categories?
Yeah, so I mean, traditionally in the old days, what we used to do is like public service ads, like give money to charity or something like this. But what I usually do is that instead of just using a placebo, I can actually use it as a test for another app.
Okay, cool, thanks.
Hello, many thanks for a nice talk.
Thank you.
So I'm also building a recommender system using Spark, and one of my biggest pains is that MLlib just offers one algorithm, namely the ALS.
The ALS, yes.
So did you build any other algorithms? Like
no, we were not building. I mean, we actually experiment. I think the ALS is essentially all what it does is that you're trying to minimize the mean squared error of a reconstruction. So I mean, essentially, you could even do like a conjugate, like you can do like a stochastic gradient to try to do that. I mean, you can even do like a random, like a gradient method. So to answer your question, no, we did not experiment with other alternatives other than the ALS, no.
Thanks.
I just want to make sure we're time.
Okay, so first of all, I wanted to say you have great presentation. It was very interesting. In Viber, I work for Viber, and we've implemented pretty much the same architecture on the same...
Can you speak up? I can't hear you from here very well, sorry.
Okay, so I work in Viber, and we implemented pretty much the same architecture on the same scale, and I wondered what BLAS library did you use, and how much resources did you use when you recorded the measures?
Okay,
One of the
so the answer for BLAS, so the BLAS comes as part of NumPy. So if you look at my code, essentially what I do, all what you have to do is that you have to import NumPy. So I was using PySpark, so all what you have to do is import NumPy, or SciPy for that matter, and both of those have BLAS-free under the hood. So you don't have to worry about that. And what was the second question? Oh, okay, so what is the side? Okay, so if I remember correctly, I can't remember like the number of executors, so maybe it was like 15 executors or something. It wasn't actually that hard. I mean, so it wasn't really that hard. And even the prediction time, I mean, I think the prediction time, we even used fewer resources than the actual training time. So it wasn't that complex.
Thanks. So I have one more question. After you compute the recommendations,
Can you speak?
after you compute the recommendations in these 8 minutes, do you persist them and then you serve them from a database, or?
So after I compute the recommendation, essentially the collaborative filtering stores it in a matrix factorization object. So I pull those back and then I compute the recommendations. And then what I do is that I then start to rank those recommendations. So for every user now, I have a vector of length 50,000 of all the apps that we have. I do a random sample to look at the distribution of the recommendations, so to get sort of like the normal distribution, and then I say, okay, I'm only going to recommend apps for users whereby I'm confident that with 95% confidence that this is more likely to be installed than not.
And this is persisted to some database where you serve it out of it.
So actually I do it online, so I don't even need to persist it because all what I need to do is that I need to immediately just get the top apps for the recommendation. So you have time for just one more question?
Sure, we have one more.
It's kind of related to the last one. But you do actually compute all combinations of users and apps. So did you ever consider to just like do it on the fly, basically when a user comes in, then
Yeah, very good
compute?
question.
Yeah?
Yes, you could do this, but what we're trying to do is that the computational cost of doing this is horrendous. Okay, so you don't really have time to do it on the fly. So we're actually doing the opposite. We're computing it offline, we're filtering out 95% of the noise, and then we're only getting the recommendations where the user comes. So we know that when you come, here's the app that we're going to show it to you right away. We couldn't do this because of the latency requirements. Yes, that's the problem. Okay, so I guess with this, I think my time is up. Thank you very much.
Give a round of hand.